And now in this lecture we'll answer on two questions. In the first question, we'll find out the size of this angle x, and in the second question, we'll find out the area of the green shape. So we'll start with the first question. In the drawing, we have a quarter circle. A or B is a quarter circle. Therefore, this angle A or B is equal to 90 degrees in size. This is angle APQ, that is also a right angle. We also know that AP equals to PQ. And again, our task is to find out the size of this angle PQB is equal to X. We have to find out the size of angle X. So we start. In the first step, we will complete the quarter circle to a semicircle. And we define this point as point M. So actually AM is the diameter of this semicircle according to our construction. So I write down AM is the diameter of this semicircle according to our construction. AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. So we have peripheral angle APL. Peripheral angle APL is equal to 90 degrees in its size according to what is given as the question, and peripheral angle APL subtend on AL. Peripheral angle APL subtend on chord AL. And again, according to our assumption, the extended line segment PQ touches the semicircle at point N, and therefore peripheral angle APL subtend on chord AL. But chord AL is definitely not the diameter of this semicircle. Why chord AL is not the diameter of this semicircle? Because of the fact that chord AL doesn't pass through point O, that is the center of the semicircle. And we know that the diameter of any circle or a semicircle must pass through the center of the circle or semicircle. So AL is not the diameter of the semicircle, and we have rule 5. It is actually contradicts rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the semicircle, but AL is not the diameter of the semicircle, therefore we have contradiction to rule 5. So please click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle AOB that is equal to 90 degrees in size, and therefore it subtends on AB, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. But here we have peripheral angle APL that is equal to 90 degrees in size, and still it doesn't subtend on the diameter of the semicircle. It subtends on AL, that is definitely not the diameter of the semicircle. Therefore, it is actually impossible that the extended side PQ will touch the semicircle at point M. So in the next step, we will assume that the extended side PQ will touch the semicircle at this point H. And again, the extended side PQ will touch the semicircle at this point H. So we have here peripheral angle APH that is equal to 90 degrees in size, and peripheral angle APH subtend on chord AH. Peripheral angle APH subtend on chord AH. But AH is definitely not the diameter of the semicircle, because AH doesn't pass from point O, that is the center of this semicircle. So AH is definitely not the diameter of this semicircle, therefore we have contradiction to rule 5 again, because we have peripheral angle APL, that is a right angle, and since it doesn't subtend on the diameter of the semicircle, because AH is not the diameter of the semicircle. So therefore we have to conclude that the extended side, due to the contradiction to rule 5, we have to conclude that the extended side PQ will touch the semicircle at point M and not in any other point. Again, the extended side PQ will touch the semicircle at point M and not in any other point. Now we don't have any contradiction to rule 5 anymore, because we have peripheral angle APM that is equal to 90 degrees in size, and peripheral angle APM subtend on AM, that is the diameter of the semicircle according to our construction. Therefore, the extended side PQ must touch the semicircle at point M. In the next step, we join points A and Q together by straight line. By joining points A and Q, we granted the right and associated triangle, triangle APQ. Triangle APQ is right angle because angle APQ is right angle, and triangle APQ is also an associated triangle because side AP equals to side PQ. So side AP equals to side PQ, and we have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. We also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle APQ. The sum of the angles in triangle APQ must be equal to 180 degrees. So which angles we have in the right triangle, triangle APQ? We have this angle that is a right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract 90 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So if you found out that the missing angle alpha equals to 45 degrees in its size, this is also angle alpha that equals to 45 degrees in its size. In the next step, we will prove that the upper right triangle AQO can go into the lower triangle OQM according to side angle side rule. Okay, again, we will prove that those two right triangles can go into each other according to side angle side rule. So I write it down. We prove that the upper right triangle AOQ can go to the lower right triangle OQM according to side angle side rule. So why those two triangles can go into each other. First of all, side AO or the right triangle AOQ equals to side OM or the right triangle OQM. They are both the radii of the semicircle, therefore they are equal to each other. So if we define the radius of the semicircle as R, then AO equals to R and OM also equals to R. So AO equals to OM equals to R. And again, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. They are both the radii of the circle, therefore they are equal to each other. In addition, those two angles, they are both right angles, and therefore they are equal to each other. So angle AOQ on the right triangle AOQ equals to angle MOQ on the right triangle OQM. So repeat again, if we found out that angle AOQ of the right triangle AOQ equals to angle MOQ of the right triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, OQ is the common side that belongs to both triangles. So you can write down that OQ equals to itself is the common side that belongs to both triangles. So again, if we found out that OQ equals to itself is the common side that belongs to both triangles. So if you prove that those two right angles can go into each other according to side angle side rule. So write it down. The right triangle AOQ congruent, this is the sign of congruent, to the right triangle OQM according to side angle side rule. That is to say that we found out that those two sides and the angle that is included between those two sides in the right upper triangle A or Q are corresponding equal to those two sides, and the angle that is included between those two sides in the lower right triangle or QM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive that side AQ of the right triangle A or Q is equal to side QM of the right triangle or QM. It again, from the fact that those two right triangles can go into each other, we derive that side AQ of the right triangle A or Q is equal to side QM of the right triangle or QM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other and their lengths. So side AQ equals to side QM. So if we focus on the right of the big associated triangle AQM, we have the rule that states that in front of equal sides in the triangle there are equal angles. So if in relation to the big associated triangle AMQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in the next step, I'll present to you a new rule, and we will implement the new rule in our drawing. The new rule is actually rule 8. So according to rule 8, an external angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. Again, an external angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So in the drawing we have triangle ABC. Triangle ABC could be any triangle. Inside triangle ABC we have three angles, alpha, beta, and gamma. Those three angles are defined as interior angles of triangle ABC because of the fact that they are located inside triangle ABC, while this is angle ACF that is defined as an external angle because of the fact that it is located outside triangle ABC. We define the external angle ACF as E. So what is the size of the external angle? Angle E. According to this rule 8, the size of this external angle E is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma, it is definitely adjacent to angle E. The two other interior angles that are not adjacent to it are those two angles, alpha and beta. So according to this rule 8, the size of the external angle E is equal to the sum of the two interior angles that are not adjacent to it. That is to say, it is equal to alpha plus beta. The size of the external angle E is equal to alpha plus beta. Okay? So we can actually implement the new rule in our drawing. Why? Because in our drawing we have, this is the associated triangle AQM. The associated triangle AQM, those two angles beta, and this third angle, they are all defined as interior angles of the associated triangle AQM, while this is angle AQP that is defined as an external angle because of the fact that it is located outside the associated triangle AQM. And according to rule 8, the size of the external angle AQP is equal to the sum of the two interior angles that are not adjacent to it. The interior angle AQM, this interior angle AQM is definitely adjacent to angle AQP. The two other interior angles that are not adjacent to it are those two angles. So the size of the external angle AQP is equal to beta plus beta, according to rule 8. So I write it down. So according to rule 8, the size of the external angle AQP is equal to beta plus beta. The size of the external angle AQP is equal to the sum of the two integrals that are not adjacent to it. That is to say, beta plus beta. Beta plus beta is 2 beta. So we found out that the size of the external angle AQP is equal to 2 beta. But we have only found out that angle AQP equals to 45 degrees in size. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divide this equation by 2. And finally we get that angle beta equals to 45 degrees over 2 is 22.5 degrees. So actually we found out that angle beta equals to 22.5 degrees in its size. So actually this is angle beta that is equal to 22.5 degrees in its size. And this is also angle beta that is equal to 22.5 degrees in its size. In the next step, we will focus on the right triangle OQM. In the right triangle OQM, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle OQM? You have this angle that is a right angle. This is angle beta that is equal to 22.5 degrees in its size. Plus this missing angle, that is angle OQM. In total, the sum of those three angles must be equal to 180 degrees. So if it again in the right triangle OQM, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus 22.5 degrees plus the size of the third missing angle OQM. In total, they must be equal to 180 degrees. Here we will subtract 90 degrees from this equation. And we get that 180 degrees minus 90 degrees is 90 degrees. And it is equal to 22.5 degrees plus the size of the missing angle OQM. Here we will subtract 22.5 degrees from this equation, and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So if we found out that the size of this that the size of this missing angle OQM is equal to 67.5 degrees. We also have the rule that says that vertex angles are equal to each other. Actually, those two angles, alpha and beta, are defined as vertex angles, and they are equal to each other in their sizes. So alpha equals to beta. Here we have also the other pair of two vertex angles that we define this angle. This is angle 1, this is angle 2. Those are the other two vertex angles that are also equal to each other in their sizes. So angle 1 equals to angle 2 because both of them are defined as vertex angles. So we can implement the rule in our drawing. One put in our drawing. We have those two angles that are defined as vertex angles. And they are equal to each other. That is to say, angle X equals to 67.5 degrees in its size. So write it down. According to the rule that vertex angles are equal to each other, we will get that angle X equals to 67.5 degrees in its size. And that is the answer to the question. So we should find out that the size of the angle that we are looking for, that is actually angle P cubic is equal to X is equal to 67.5 degrees in its size. This is the answer to the first question. In the next step, I will present to you the second question and we will solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. So in the drawing, we have a semicircle. The diameter of this semicircle PQ equals to 10 units in length. Therefore, the radius is 5. So the radius of this semicircle equals to 5 units in its length. So write it down. The radius equals to 5. In addition, inside this big semicircle, we have the big square ABCD and we have the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we will define the center of this semicircle. This point is point O. We will join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of this semicircle that is equal to 5 units in its length. Likewise, we join points O and E together by a straight line. OE is of course the radius of the semicircle that is equal to 5 units in its length. MEFC is a square, and therefore this angle must be equal to 90 degrees in its size, according to the rule that all the angles inside the square are right angles. Likewise, ABCD is also a square, and therefore this angle must be equal to 90 degrees in its size. In the next step, we will define the length of one side of the big square ABCD as A. So actually, AB equals to AD equals to DC equals to BC equals to A, because all the sides of any square are equal to each other in their lengths. We will define the length of this short line segment OC as X. So what is the length of the missing line segment BO? From the domain it is very easy to see that BO equals to BC minus OC. So write it down. BO equals to BC minus OC. So BO equals to BC, BC is A, minus OC, OC is X. So in total, BO equals to A minus X units in its length. BO equals to A minus X. CF equals to B unit, Actually, we define one side of this small square MECF as B. Therefore, CF is B. EF is also B. ME is B, and MC is also B. So, in the next step, I'll copy the right triangle ABO in a new page and implement the Pythagoras theorem on the right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AO of the right triangle ABO is equals to 5 units in its length. This is actually, of course, also the radius of the semicircle. AB equals to A units in its length. BC equals to BO equals to A minus X units in its length. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right triangle ABO that is coming from the original drawing. In this right triangle ABO, according to the Pythagoras theorem, AO square, that is the square of the hypotenuse, equals to AB square plus BO square. So I write it down. This will be equation 1. According to equation 1, AO square, that is the square of the hypotenuse, is equal to AB square plus BO square. The hypotenuse AO equals to 5 units in its length, therefore AO square is 5 squared, that is 25, and it is equals to AB square. AB is A, therefore AB square is A square plus BO square. BO equals to A minus X, therefore BO square equals to A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A square plus A minus X squared. In the next step, I'll copy the right triangle OEF in a new page and we'll implement on it the Pythagoras theorem. Here by PT, abbreviation for Pythagoras theorem. The hypotenuse OE equals to 5 units in its length, EF equals to B, and OF equals to, OF in total equals to X plus B. So actually, this is the right triangle EOF, this is coming from the original drawing. According to the Pythagoras theorem, in this right triangle EOF, EO squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down, this will be equation 2. According to equation 2, OE squared, that is the square of the hypotenuse, is equal to EF squared plus OF squared. The hypotenuse O equals to 5 units in its length, therefore OE squared is 5 squared, that is 25. And it is equals to EF squared. EF is B, therefore EF is B, therefore EF squared is B squared. Plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So if we found out that according to equation 2, 25 equals to B squared plus X plus B squared. This is according to equation 2, while according to equation 1, if we found out that 25 equals to A squared plus A minus X squared. In the next step, we'll create equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. So according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. (25) according to equation 1 is equal to A squared plus A minus X squared. And it is equal to 25 according to equation 2. 25 according to equation 2 is equal to B squared plus X plus B squared. So in total, if we found out that according to equation 2, A squared plus A minus X squared equals to B squared plus X plus B squared. Here we will open the brackets on both sides of this equation, equation 3, and we get that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X, and it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation, so X squared will get cancelled. After we cancel X squared, in this side of equation 3 we have A squared plus A squared, that is 2A squared minus 2AX, and it is equals to, in the other side of this equation 3 we have B squared plus B squared, that is 2B squared plus 2bx. So here we will add 2ax to this equation, equation 3, and we get that according to equation 3, 2a squared equals to 2ax plus 2bx plus 2b squared. So if you found out that according to equation 3, 2a squared equals to 2ax plus 2bx plus 2b squared. Here we will subtract 2b squared from this equation, and we get that according to equation 3, 2a squared minus 2b squared equals to 2ax plus 2bx. So here we will divide this equation 3 by 2, and we get that according to equation 3, 2a squared over 2 is a squared, minus 2b squared over 2 is minus b squared, and it is equal to 2ax over 2 is ax, and 2bx over 2 is bx, so it is ax plus bx. We have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. So a squared minus b squared equals to a plus b times a minus b. Here we have ax plus bx. So we take x as a common factor from those two expressions. Inside the brackets we left only with a plus b. So in total we found out that a plus b times a minus b equals to x times a plus b. Because of the fact that a is the length of the big square, the length of one side of the big square, ABCD, and b is the length of one side of the small square, MEFC. So a and b are the lengths of the squares, and therefore they are positive numbers. And when you add two positive numbers to each other, the result is a positive number. That is to say, a plus b can never be equal to 0. A plus b can never be equal to 0, and therefore it is allowable to divide this equation 3 by a plus b. So we divide this equation 3 by a plus b. So in this side of the equation, a plus b will get cancelled, and we left only with a minus b. In this side of the equation, a plus b also will get cancelled, and we left only with x. So in total, according to equation 3, we have found out that a minus b equals to x. So here we will add b to this equation, equation 3, and we get that according to equation 3, a equals to b plus x. So here we subtract x from this equation, equation 3, and we get that according to equation 3, we subtract x from this equation 3, and we get that according to equation 3, a minus x equals to b. According to equation 3, we found out that a minus x equals to b. Here we square this equation 3. We square both sides of this equation, equation 3. And we get that a minus x squared equals to b squared. But again, according to equation 3, we found out that a minus x squared equals to b squared. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total is equal to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MECF. So repeat again. We actually found out that the area of this green shape, that is the area that we are looking for in this question, is equal to the area of the big semicircle minus the area of the big square minus the area of the small square. So what is the area of the big semicircle? Actually, we know that the area of any semicircle equals to the area of the circle over 2. So the area of the semicircle must be equal to the area of the circle pi r square over 2. And again, the area of the semicircle equals to pi r square over 2. But r equals to 5. The area of the semicircle equals to pi r square over 2. R equals to 5. Therefore, r square is 5 squared. This is 25. So in total, this expression equals to 25 pi over 2 square units. So if we found out that the area of the big semicircle is equal to 25 pi over 2 square units in its size, minus the area of the big square ABCD. We know that one side of square ABCD is equals to a units in its length, and the area of any square equals to the length of one side squared. So the area of the big semicircle equals to a squared minus the area of the small square. We know that one side of the small square, the length of one side of the small square is b, so the area of the small square is b squared. So it is minus b squared. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus a square minus b square. So here we take minus 1 as a common factor from those two expressions and get the area of the green shape in total equals to 25 pi over 2. So we took minus 1 as a common factor from those two expressions. So inside the brackets we have a square plus b square. So the area of the green shape in total equals to 25 pi over 2, that is the area of the semicircle, minus a square plus b square. What is the value of a square plus b square? We have, according to equation 1, we actually found out that 25 equals to a square plus a minus x square. Again, according to equation 1, we found out that 25 equals to a square plus a minus x square. But we have only found out that a minus x square equals to b square. According to equation 3, a minus x square equals to b square. So we can substitute a minus x square here by b square. If we do it now, we get that according to equation 1, 25 equals to a square plus a minus x square, and a minus x square is b square. So in total we should find out that a square plus b square equals to 25. So we can substitute a square plus b square in this expression by 25. We do it now, then we get actually the area of the green shape in total equals to 25 pi over 2, that is the area of the semicircle, minus a square plus b square. But a square plus b square equals to 25, so we substitute a square plus b square in this expression by 25. So in total we actually found out that the area of the green shape equals to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the value of this expression is equal to 14.27 square units in its size. So repeat again, we actually found out that the area of this green shape is equal to either 25 pi over 2 minus 25 square units, or in terms of numbers, the area of this green shape is equal to 14.27 square units in its size. So we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the size of this angle PQB is equal to x. We have to find out the value of angle x. So in the drawing we have a semicircle, AOB is a semicircle, therefore this angle is a right angle. In addition, we know that angle APQ is also a right angle, and we also know that AP equals to PQ. Again, our task is to find out the size of angle PQB is equal to x. We have to find out the size of angle x, or the value of angle x. So first of all, we completed the quarter circle to a semicircle, and we define this point as point M. So actually, AM is the diameter of the semicircle according to our construction. Repeat again. AM is the diameter of the semicircle according to our construction, because we completed the quarter circle to a semicircle. AM is the diameter of the semicircle. AM is the diameter, it is absolutely a straight line. So if you focus on the right, although it doesn't look like a straight line here, but it is the problem of the drawing itself. AM is definitely a straight line, it's a diameter. So if you focus on the right side of the straight line AM at point O. Here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we extended line segment PQ by straight line until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at point L. Again, the extended line segment PQ will touch the semicircle at point L, according to our assumption. So we created here peripheral angle APL. This is peripheral angle APL. This is equals to 90 degrees in size, according to what is given as the equation. Peripheral angle APL equals to 90 degrees in its size. It is a peripheral angle here, angle APQ. Therefore, it is peripheral angle APL is equals to 90 degrees in its size. And peripheral angle APL subtend on AL. Again, peripheral angle APL is equal to 90 degrees in size, subtend on chord AL. But AL is definitely not the diameter of the semicircle. Why chord AL is not the diameter of the semicircle? Because chord AL doesn't pass from point O, that is the center of the semicircle. You know that any diameter pass through the center of the semicircle. And because of the fact that AM doesn't pass through point O, that is the center of the semicircle, it cannot be the diameter of the semicircle. So we have a contradiction to rule 5. Because according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the semicircle. But AL, so peripheral angle APL subtend on AL, that is definitely not the diameter of the semicircle. So it is a contradiction to rule 5. So the assumption that the extended side PQ will touch the semicircle at point L is incorrect assumption. So therefore, we assume that the extended side PQ will touch the semicircle at this point H. We touch the circle at point H. Okay, we assume that the extended side PQ will touch the circle here at point H. Okay, so according to our assumption, we have here peripheral angle APH that is equal to 90 degrees in its side according to what is given as the equation. And peripheral angle APH subtend on chord AH, of course. Again, peripheral angle APH subtend on chord AH. But again, we have contradiction to rule 5 because AH is definitely not the diameter of the semicircle. Why AH is not the diameter of the semicircle? Because AH doesn't pass through point O, that is the center of the semicircle. So AH cannot be the diameter of the semicircle because it doesn't pass through point O, that is the center of the semicircle. So due to those contradictions, our assumption that the extended side PQ will touch the semicircle at point H is not correct. It's incorrect assumption. Therefore, we can conclude from what we did until now that the extended side PQ will touch the semicircle at point M and not in any other point. Otherwise, we have contradiction to rule 5. So if the extended side PQ will touch the semicircle at point M, we don't have any contradiction to rule 5. Because we have peripheral angle APM, that is equal to 90 degrees in size according to what is given as the equation, and peripheral angle APM subtend on AM, that is the diameter of the semicircle, exactly according to rule 5. Okay? So in the next step, we join points A and Q together by straight line. By joining points A and Q, get the right triangle APQ. It is given as a question that AP equals to PQ. So in relation to the right and associated triangle APQ, we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the right and associated triangle APQ, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle APQ. The sum of the angles in the right triangle, in the right and the associated triangle APQ must be equal to 180 degrees. So which angles we have in the right and associated triangle APQ? We have this angle, that is the right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract the 90 degrees from this equation. If I found out that 180 degrees minus 90 degrees is 90 degrees, so 2 alpha equals to 90 degrees. Here we divided the equation by 2 and found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. This is angle alpha, that is equals to 45 degrees in its size, and this is also angle alpha, that is equals to 45 degrees in its size. In the next step, we prove that those two right angles can go into each other according to side angle side rule. We can prove that the right upper triangle AOQ can go into the right lower triangle OQM according to side angle side rule. So why those two right angles can go into each other? First of all, AO, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. They're above the radii of the semicircle, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, OQ is a common side that belongs to both triangles. So OQ equals to itself is a common side that belongs to both triangles. So we should prove that those two right triangles can go into each other according to side angle side rule. Okay, again, we should prove that the right upper triangle AOQ congruent, this is the sign of congruent, to the right lower triangle OQM according to side angle side rule. That is to say, we should prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right triangle OQM. Therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. Again, we derive that AQ equals to QM according to the rule that says that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. Okay, so AQ equals to QM. So if we relate to the big associated triangle MAQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 8. According to rule 8, the external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. Again, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the drawing, we have triangle ABC that could be any triangle. Those triangles alpha, beta, and gamma are defined as interangles of triangle ABC because of the fact that they are located inside triangle ABC. While this is angle ACF, this is equal to A according to our definition. Angle E is defined as an external angle because of the fact that it is located outside triangle ABC. And according to this rule 8, the size of the external angle ACF is equal to A according to E according to our definition. Angle E equals to the sum of the two interangles that are not adjacent to it. This is the interangle gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to angle E are those two angles alpha and beta. So according to this rule 8, the size of the external angle E equals to the sum of the two interangles that are not adjacent to it. That is to say, it is equals to alpha plus beta. So angle E equals to alpha plus beta. So we implemented the new rule in our drawing. In our drawing, if we relate to the associated triangle AQM, we have those three angles are defined as interangles. This is angle AQP. It is defined as an external angle because it is located outside the associated triangle AQM. So according to rule 8, the size of the external angle AQP is equal to the sum of the two interangles that are not adjacent to it. This angle AQM is definitely adjacent to angle APQ. The two other interangles that are not adjacent to angle AQP to this angle are those two angles, beta and beta. Therefore, according to rate, the size of the external angle AQP must be equal to the sum of the two external that are not adjacent to it. That is to say, it is beta plus beta. So in total, according to rate, we actually found out that the size of the external angle AQP is equal to beta plus beta. But again, according to rate, if we relate to the associated triangle AQM, the size of the external angle AQP of the associated triangle AQM is equal to the sum of the two triangles that are not adjacent to it. That is to say, it is beta plus beta. Beta plus beta is 2 beta. So the size of the external angle AQP is equal to 2 beta. But we have only found out that the size of the external angle AQP is equal to 45 degrees. So we can solve the angle AQP, the external angle AQP by 45 degrees. We did it, and if we found out that 45 degrees equals to 2 beta, here we divided this equation by 2, and we found out that angle beta equals to 25 degrees over 2. 25 degrees over 2 is 22.5 degrees. So if we found out that the size of this angle beta is equal to 22.5 degrees, and this is angle beta is equal to 22.5 degrees. In the next step, we focus on the right triangle OQM. In the right triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is the right angle. This is an angle beta that is equal to 22.5 degrees in size. This is the missing angle OQM. So in total, the sum of those angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle OQM, the sum of the triangles must be equal to 180 degrees. That is to say, 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, in total they must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally found out that 180 degrees minus 90 degrees is 90 degrees. So 22.5 degrees plus the size of the missing angle OQM, in total must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation, and finally found out that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is equal to 67.5 degrees. So actually this is the missing angle OQM that is equal to 67.5 degrees in size. So we have the rule that says that vertex angles are equal to each other. Those two angles are defined as vertex angles, therefore they are equal to each other. That is to say, angle alpha equals to angle beta. Those two angles are also defined as vertex angles, and therefore they are equal to each other. That is to say, angle 1 equals to angle 2. We can implement the rule in our drawing. One because in our drawing we have those two vertex angles that are equal to each other in their sizes. That is to say, angle x equals to 67.5 degrees in size. If we found out that the missing angle x, according to the rule that vertex angles are equal to each other, we find out that the missing angle x is equal to 67.5 degrees in its size. So we finished with the first question. In the next step, I present to you the second question. We solve the second question of this lecture. The second question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle. The diameter of this semicircle PQ equals to 30 units in itself, therefore the radius is 5. In addition, we know that inside this big semicircle, we have the big square ABCD, and we have also the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by side line. OA is of course the radius of this semicircle, that is 5. We join points O and D together by side line. OE is also the radius of the semicircle, that is equal to 5. The next step, we define the length of one side of the big square ABCD as A. Therefore, AB equals to BC equals to CD equals to DA equals to A. We define the length of the short line segment OC as X. Therefore, the missing line segment BO must be equal to BC minus OC. Again, BO equals to BC minus OC. So BO equals to BC, that is A, minus OC, that is X. So in total, BO equals to A minus X units in its length. ABCD is a square, therefore this angle is a right angle. We know that also MEFC is also a square, therefore this angle is a right angle. We define one side of this small square MEFC as B. So ME equals to EF equals to FC equals to B. In the next step, I copied the right triangle ABO in a new page and implemented the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, this is the right triangle ABO. This is the copied from the original domain. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25, and this is equals to AB squared. AB is A, therefore AB squared is A squared, plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. Likewise, I copied the right triangle OEF in a new page and implemented the Pythagoras theorem on this right triangle OEF. This is the right triangle OEF that I copied from the original domain. In this right triangle OEF, according to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. OE is 5, therefore OE squared is 5 squared, that is 25, and it is equals to EF squared. EF is B, therefore EF squared is B squared, plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So in total, according to equation 2, we actually found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, while according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. So we have two equations. Therefore, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Again, according to the further equation that we created, according to the further equation, 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared, and it equals to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So in total, we should find out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here, open the brackets on both sides of this equation, equation 3, and we found out that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared plus 2 times A times X. And it is equals to B squared plus X plus B squared. So it is B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. Here we have X squared on both sides of this equation, so X squared will get cancelled. After we cancel X squared on this side of the equation, we have only with A squared plus A squared, that is 2A squared, minus 2AX. While in the other side of this equation 3, we have B squared plus B squared, that is 2B squared, plus 2XB. Here we added 2AX to this equation, equation 3, and found out that according to equation 3, 2A squared equals to 2AX plus 2XB plus 2B squared. Here we subtract 2B squared from this equation, equation 3, and we found out that according to equation 3, 2A squared minus 2B squared equals to 2AX plus 2BX. Here we divided this equation, equation 3 by 2, and found out that the 2A squared over 2 is A squared, minus 2B squared over 2 is minus B squared, and it is equals to 2AX over 2 is AX, plus 2BX over 2 is BX. So in total, according to equation 3, we actually found out that A squared minus B squared equals to AX plus BX. We have the famous algebraic identity that says that A squared minus B squared equals to A plus B times A minus B. And it is equals to AX plus BX. Here we took out X as a common factor from those two expressions, so inside the brackets we have A plus B. So in total, we actually found out that A plus B times A minus B equals to X times A plus B. A and B are the rest of the squares, the big square and the small square, and therefore absolutely a positive numbers. And when you add two positive numbers to each other, the result must be a positive. That is to say, A plus B must be a positive number. It can never be equal to 0. Therefore, it is allowable to divide this equation 3 by A plus B. So we divided the equation 3 by A plus B. So here A plus B will get cancelled, and we have to leave A minus B. In the other side of the equation, A plus B also will get cancelled, and we have to leave with X. So total, according to equation 3, we actually found out that A minus B equals to X. Here we added b to this equation 3 and finally found out that a equals to b plus x. Here we subtract x from this equation 3 and finally found out that a minus x equals to b. So here we squared both sides of this equation and finally found out that a minus x squared equals to b squared. So according to equation 3, we actually found out that a minus x squared equals to b squared. Our test is to find out the area of this green shape. So what is the area of the green shape? From the moment it's very easy to see that the area of this green shape is equal to the area of the big semicircle minus the area of the big square minus the area of the small square. So again, the area of this green shape in total is equal to the area of the big semicircle minus the area of the big square minus the area of the small square. The area of the big semicircle equals to the area of the circle over 2. That is to say, it is pi r square over 2. But r is 5, therefore r squared is 5 squared, that is 25. So in total this expression equals to 25 pi over 2. So the area of this semicircle in total is equals to 20 pi over 2 square units in its size. Minus the area of the big square, ABCD. One side of the big square, ABCD, is 8, therefore the area must be equal to a square, so it is minus a square minus the area of the small square. One side of the small square is equal to b units in its graph, therefore the area of the small square is b square, so it is minus b square. So here we took minus 1 as a common factor from those two expressions, so in total we found out that the area of the green shape equals to 25 pi over 2, that is the area of the semicircle. Here we took minus 1 as a common factor from those two expressions, so inside the brackets we left with a square plus b square. According to equation 1, we have found out that 25 equals to a square plus a minus x squared. And we have already found out that a minus x squared, according to equation 3, a minus x squared equals to b squared. Therefore, we can substitute a minus x squared in this equation 1 by b squared. We did it, and we have found out that 25 equals to a squared plus a minus x squared, it is b squared. So in total, according to equation 1, we have found out that 25 equals to a squared plus b squared. Therefore, we can substitute a squared plus b squared in this expression for the area of the green shape. We can substitute a squared plus b squared by 25 from equation 1. We did it, and we found out that the area of the green shape in total equals to 25 pi over 2 minus a squared plus b squared. A squared plus b squared is 25. So in total we found out that the area of the green shape, that is the area that we are looking for in this question, is equal to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the area of this green shape is equal to 14.27 square units in its size. Okay, thank you very much.